So hi everyone, it looks like it's a good crowd. Thank you very much for coming. And let me thank the organizers, Laurie, and the other members of the HDF group for letting me give this presentation. HDF5 has been central to our work for actually pretty well for over 20 years. I don't know when it first was released, but we've been using it in the Nexus world since at least 2001, if not earlier. But this is not going to be a talk about Nexus specifically. I should introduce myself. Sorry, I'm Osborn. I'm a scientist at Argonne National Lab, so I'm not a computer programmer, although I do quite a bit of Python programming mostly now. My background is mostly in neutron and X-ray scattering. And in recent years, we've been collecting larger and larger volumes of data, and we've needed to develop the tools that allow us to cope with this torrent. And this is data where we don't have some standard process that will reduce it down to a reasonable size. We often have to look at the data in flexible ways in order to understand what on earth it means before then perhaps developing scripts to produce a final analysis. So we do actually have a standard workflow, but we don't have a standard way of analyzing the data. And NeXpy is designed to be a GUI toolbox that allows us to analyze it. And although it was, as its name implies, it focuses on the Nexus data format, which is something I've been involved in for actually since its inception nearly 30 years ago. Actually, it will be 30, no, yeah, it's nearly 30 years ago. Nevertheless, all Nexus files are now stored as HDF5 files, and most of the aspects of most of the tools are actually fairly generic. You can read virtually any HDF5 file and ignore the Nexus trappings, except for a couple of things I'll mention. Now, there are a lot of you, I can only see a few of you. I don't think I'll be able to see hands up, things like that. So Laurie, would you, if you see something in the chat or if somebody puts a hand up, could you interrupt me at any time?
Yes, yep, will do.
Okay, so let's get going. Now, as I say, this talk is not about Nexus. But on the other hand, I think it won't be really comprehensible unless I say one or two things about Nexus. I'm not sure if you've had talks within the HDF5 group about Nexus specifically. So anyway, I've just got a couple of slides which just explain a little bit about what it is. So Nexus files, as I say now, are all stored as HDF5. But what they do is they add just some semantics. Those are design rules, which mean that you can open any Nexus file without looking at any documentation and have a reasonable idea of what it contains and what the different components mean. As I say, the purpose of these rules is to make them self-describing. Nexus uses a hierarchical design, as befits HDF5. And as you all know, that means that it's much like a file system. You can refer to elements of it using sort of POSIX-style file paths. And it means that you can put important data at a very high level of the file, and you can store arcane details of the different calibration parameters that you only need for some diagnostics. Say you can bury them deep within the file. And there are what are called base classes, which define glossaries of terms. So if you're going to store the temperature in a file, then it will tell you what sort of group to put that in and call it temperature. You don't call it temp, whatever. Okay. If you're not familiar, I mean, Nexus is now actually pretty well established. Excuse me, I'll pour some tea. It has a international advisory committee, which represents I don't know, nearly 20 or so major facilities all around the world. It's the official archive format at a number of facilities. It's mostly used by neutron and X-ray scatterers, but actually people in the MUSR community have been using it for quite a while, and also electron microscopy communities have just recently expressed interest. And in principle, it could be extended to other experimental techniques as well. And as I say, the NIAC, as it's called, is very active. We had a meeting only a couple of months ago. And it reaches out to things like detectors who make X-ray detectors. They use HDF5 for their detector storage now for the latest generation of detectors, but they worked with the committee to make sure that that data was Nexus compliant. So this just shows you the worldwide reach of the committee, which is now run by Aaron Brewster, Lawrence Berkeley. It was run by Ben Watson, Swiss Light Source recently, so it's a really international effort. And this just gives you a flavor of what a Nexus file might look like. So just like HDF5 files, actually the Nexus design came before HDF5. We did use HDF4, but unfortunately it maps exactly onto what HDF5 provides. So we have groups, just as HDF5 files do. We have fields, which is what we call datasets, and both groups and fields can have attributes. And we store it in a hierarchical format. So there's usually a high-level group, which is, here is called scan_1. Now it's got a class. So HDF5 doesn't actually have the concept of classes, I believe, but, well, if it doesn't. But so this is done by putting in an attribute which defines what class it is. And the Nexus Format API, the Python API, which I'll be talking about, actually explicitly instantiates these as classes, which are subgroups of the NX group class. So that's just so you know, but the idea is an entry is a top level class, and that entry can contain all the information you need to understand a particular measurement. For instance, the sample information, you might want to store the temperature. You're asked to put that into an NX sample class. There's a lot of arcane instrumental details you may never want to know about, which you put in an NX instrument class. And then this NX data class, which is actually the core of it. And this is probably the only class that if you're not interested in Nexus, that is worth finding out a little bit more about. And I think, well, okay, yeah, this is not quite the slide I thought it was going to be, but anyway, so as I say, we have a Python API. NeXpy itself is a GUI using PyQt, but underneath it, it uses a separate package called Nexus Format, which you can install separately if you have no interest in using the GUI. But why is this not advancing? Okay, well, anyway. So, and the feature of the GUI is that you can load an entire tree. Of course, the GUI, sorry, not the GUI, the feature of the API, you can load an entire tree because it's using H5 Pi underneath. So it's basically a thin layer on top of H5 Pi. But it loads it lazily. It loads everything except for the large arrays, so that you have access to the entire tree as a kind of memory map of the entire file the minute you load it. And so, for instance, you can use the POSIX file path to say to read data or to access data stored within that tree immediately. And it maps all Nexus objects into Python objects. So the groups are effectively dictionaries with a certain class added to it. The fields are usually NumPy arrays, so they can be scalar strings or other. We don't actually handle compound data sets, although if you read them in, they will be the underlying NumPy data will be there, and then attributes. For instance, and the reason why we have fields on top of NumPy arrays is because fields can have attributes attached to them, which you can't with NumPy arrays. Okay, and it makes it easy to create standard conforming Nexus structures. And the NX data group, which I thought I was going to describe now, is one of them. And here it is. Okay, so the NX data group is the one class that might be of use, because what it does is it encapsulates everything that constitutes plottable data. The definition of these actually goes right back to the beginning of Nexus. So they preceded, for instance, dimension scales, which try and do something similar. But the idea of the group is that it contains the data, which could be any dimension, and it contains all the axes, in this case, two one-dimensional axes, time of flight and polar angle, which, and if you plot this, then you're going to want to plot the counts against these two axes. And there are attributes defined which one is the x-axis, which is the y, etc., etc. Okay, but you can also add extra things like weights if you have normalized to weights, that it will automatically do that when you plot, and errors and other things. And the thing about it is that it's a self-contained object, which you can then, for instance, index. So now this index here is taking that two-dimensional array and extracting a certain slab from it, but it's acting on the NX data group. It's not acting on the arrays. And so not only does it index the data correctly, but it also indexes the axes. So that and I'll show you this later, but what the product of this is another NX data group, which has the right, the axes adjusted accordingly. And you can even do arithmetic operations on it, add, subtract, multiply, divide. So that if, for instance, you need to subtract a background or something, you can subtract two NX data arrays, two NX data groups, and the resulting group will have the corrected signal with the same axes assigned. And for 1D data, it means you can do some sort of statistical analyses. So you need to know what the x-axis is if you're going to calculate, say, the mean along that axis or the standard deviation, and that operates directly on the NX data class. And of course, you can plot it. Okay, I'll give examples of this later. I'm going to go through quick slides, hopefully fairly quickly, and then give some demonstrations, which may give you a better feel if this is a bit of a rush. Okay, so NeXpy. NeXpy is, as I say, a PyQt GUI, which is built on top of this Nexus Format API. And it's designed to give us a flexible toolbox for analyzing and visualizing data. So our analyses tend to be fairly chaotic. We can't sort of fit them into a nice Jupyter notebook, for instance, which tends to assume that you know exactly what you're doing. You have a linear workflow and you go from A to B. We're continually jumping backwards and forwards between different views of the data and deciding what to do next. And this NeXpy is designed to allow you to do that. And it's I say at the top there, restoring a scientist's control over their own data. I think harnessing the power of HDF5 to the convenience of Python now allows scientists to have full control of their data and to actually play with it in ways that were not possible before. We were dependent on people who knew how to program in C++ or whatever. Its original purpose was to handle neutron X-ray scattering data. It's something that we have been developing in our group for, I don't know, probably 8 or 9 years now. And it's evolved as our needs have evolved. But as I hope to show, I believe that many of the features of it could be useful to other people in the HDF5 community, and that's up to you to decide. Anyway, as I say, the overarching goal is to make it easy to play with the data. So it has tools for inspecting the components of the data, visualizing them, manipulating them, fitting them, etc. And one key thing is we collect a lot of data as a function of, say, some parametric variable like temperature. And we want to be able to see how that data is varying from one scan to the next. And so we've developed tools that allow us to compare multiple data sets. And we have the ability to develop new algorithms and modes of analysis. And I'll show something of that later. It's a pure Python package. You can install it from CondaForge or pip. It supports any flavor of PyQt at the moment, and it's dependent on some very commonly used tools in the Python community: IPython, Matplotlib, H5Py, of course, and the Nexus Format API. Okay, and there's the URL if you want to look at the documentation. So when you open NeXpy, what you do is you just get a GUI which has 3 main components. It has a tree view, and we load our files into tree view using standard open dialogues, or you can actually attach them in the shell, but that's another matter. This gives us a continual view of what the current state of the data is. Okay, so we can obviously open up different components of the tree, look at it, and as we change things, we can see how they've evolved or whatever. And we can, but a key thing is that we often just double click on things. If it's an NX data item, that will automatically generate a plot in this Matplotlib window. So we have something which is all derived from the whole Matplotlib Qt graphs, but it has other tabs, which I'll show you later. to allow you to plot the data. And then it has an IPython shell, which is connected. So the names, all of the files that have been loaded here are available from within the shell. And so you can do things either within the shell or through the GUI. Okay. And then there are other features like tooltips and ways to change the limits and blah, blah, blah. Okay. And hopefully these will all come out later in the demonstrations. So you can either directly load HDF5 files in the open file dialog, or you can import from other formats. So if your data is stored in something like Spec, I'll show an example of this to all my X-ray scattering friends later on, or CBF is another format used by X-ray scattering community. You can load this data, you can load multi-column text files, etc., and they will be pulled into the tree as a Nexus structure. And then these things I think I've said, but there are a lot of things you can actually operate on the data itself, actually directly within the tree. Okay, but as I say, all things that are in the tree are also available from the shell. And then I'll describe, I'll actually show examples of how we use various panels, which allow us to combine data from multiple data which is stored in this tree. And one of the things that we've found is that this gives us a sort of convenient GUI access to things which are available in matplotlib, but which mean that we don't have to keep on going back to the matplotlib website to remind ourselves how to do things, like how to change the color maps, or produce skew axes, or produce legends, etc. And I'll give an example of this as well. You can see it has some features of a sort of HDF view type thing where you can actually inspect the data itself within these GUI panels. Okay, so I'm not actually gonna, these are slides I prepared for when I wasn't doing a demo. Perhaps I'll come back to them if the demo crashes and burns, but we have various panels which are available from any of these plots. One of them is a projection panel, which allows us to take arbitrary cuts through the multi-dimensional data, not just the two-dimensional plots, but the full 3 or 4 or 5-dimensional data set. A fit panel, which is a GUI interface to LMFit, which is a very nice package that was developed by, the project's led by Matt Newville here at Argonne. Actually, Spec2 Nexus, which we use for importing spec files, was written by Pete Jemian at Argonne. So it makes me appreciate that. I didn't realize what a powerhouse Argonne was in the software field. But anyway, there's some very useful tools that we produced because we needed them. Anyway, and I'll actually give you an example of using this panel. There's a limits panel, which allows us to synchronously change limits on multiple data sets. And a scan panel, which allows us to combine data from lots of data sets and consolidate them into a single array using the wonders of virtual data sets, which HDF5 have provided. And hopefully I'll be able to give an example of that. Oh, and finally, we have a script editor, which is built in. And this script editor, if you run script, it will actually run everything you put in here in the shell. So everything that's loaded in the tree is accessible in this script. And so if you have lots of repetitive interaction things, or you're just trying to develop new algorithms, then you can test them by creating them as scripts and save them to a file. And actually, this turns out to be one of the most important things we did. For instance, one of the things I'm proudest of is that we had a former postdoc who's now a member of staff at the Advanced Photon Source, who, without any programming experience, taught himself enough SciPy and used the data loaded in the tree to generate a whole new way of analyzing our data. This is a fairly new technique called 3D Delta PDF, developed in ETH in Switzerland. And he experimented with different ways of implementing this, just using the script editor. And as I say, he had no programming experience, but it's now fundamental to nearly all our data analysis. Oh, okay, there's one last thing, is that, before I go on to the demos, and that is that we have a plugin architecture. So here you can see at the top here, perhaps, I don't know if you can see it on your screen, but there's this is on a Mac, okay, so it's in the top menu bar. There's a new menu item called Refine, and this is a whole workflow that we have created for analyzing single crystal diffuse scattering data, all the different components we need to analyze it. And so we have provided simple GUI interfaces to things like, this is a powder calibration, which uses some very nice software written at the European Synchrotron Radiation Facility in Grenoble, a thing called PyPhi. They have very sophisticated tools for calibrating the geometry of the detector based on these powder measurements, these rings. What NeXpy does is, what this plugin architecture does is allows us to add these GUIs, and we're operating on data that here is actually stored within the Nexus file. Sorry, within the NeXpy tree. Okay, so so if you have specialists, so in principle, NeXpy could be used as just a sort of the underlying basis for actually putting in some quite sophisticated specialist applications. Actually, I can see there are a couple of things in the chat. I don't know, are these things I should respond to?
No, well, just you'll share your slide deck, right?
Sorry? Your slide deck.
You're okay. Yeah, we'll get that, and the recording will be available too. So
okay, so just questions about. Forgive me if I'm flashing too fast. I'm happy to take questions, of course, at the end. But I wanted to. I think that is it. Yeah, that's my summary. So I'll come back to this later. Oh, there's. I wonder where the chat was. Okay, good. So, okay, so you can still see my screen, hopefully. So, so this is the demo part, where I hope things which I just sort of flashed through in the slides might become a little bit clearer. And the first thing I'm going to do is actually just to open a Jupyter console to show the Nexus format part of this in operation. Okay, so can you see the text? I don't know if it just plus works. So is that very clear?
we have a yes in the chat. Yeah, it's a decent size, yes.
Yeah, well, actually, I've just increased the size, so it should be fine. So the first thing then is this is just to show how you could use the underlying Nexus format API, which you can install without installing the GUI. And the first thing to do is to import it. Now I'm using a wildcard import, which I know is frowned upon by many in the Python community, but every single symbol that gets imported has an NX prefix. So it should be very little chance of a name clash. And that's, but that does give you the advantage of these things being fairly, you don't have to keep on importing. You don't necessarily know in advance which parts of the Nexus you need. So let me just load some data quickly. This is a file that I know exists on here. And what this has done is it's loaded the entire H5 tree. Actually, it's only really loaded the top layer, but if you want to access the rest of the tree, it's all there. So if I do that, this is the entire file, okay, in gory detail. All the attributes are stored in this long version of the tree, okay, and you can see then that it's a mixture of NX entries, NX datas, NX instruments. Everything I described in Nexus is actually here somewhere in the tree. And the minute that you load it, then objects within the tree, and you can use tab complete, like temperature, for instance, are immediately available to you. And actually, if you opened it in read-write mode, you could even then actually change these objects. And I can demonstrate that if people want, but I won't here. But you can also then, of course, look at the individual data in the tree. So the main, let's look at monitor 1, say. Actually, let me quickly plot this tree. So this monitor part of the tree, this monitor group, NX monitor is actually a subgroup of the NX data group. Okay? So here it defines that it's a one-dimensional data set. You can see here the signal is called data. The axis is called time of flight. And that means that if I wanted to just do use a plot of that, say, then it produces a sensible plot just using matplotlib. Okay. But if I was to look at, say, the data tree, we see this is two-dimensional data. So there are two axes. There's a polar angle and time-applied angle, and two-dimensional data. So if I plot this, and of course I get a two-dimensional plot. Actually, I probably want to do a log plot in this case. So now, one of the things I said about this is that in principle, you can index these groups themselves. So I could do root entry/data and just say, okay, I actually only want to have one of the axes. So I'm going to say 0, and then perhaps I only want to have 10 to 20 in along the x-axis. Okay, and that produces just another NX data group. And now the data is only 10 long. It's one-dimensional. It tells you what the average angle of the polar angle is, but which is not stored as an axis anymore. But the time of flight is length 11. So I now could just plot this data, which would actually be a bit boring, but nevertheless, you know, that data is now available as an NX data group, and I can do other things to it, like I can actually say, you know, actually I can overplot, say, not sure why I do this, but 2 times that, say, and it overplots, you know, double the counts. So you can see that the NX data group becomes actually quite a powerful object, which you can use in data analysis to produce derivative data, cutting out slabs, subtracting backgrounds, normalizing, etc., etc. Okay, so I think that's all I wanted to show in the Jupyter notebook. I don't know if there are any questions. There seems to be some couple of things. Well, okay, but let me just trust Laurie to interrupt me. I won't keep looking at the chat panel. Okay, so I'm going to exit from here. So let's run NeXpy itself. In principle, I could have run NeXpy -r and it would have loaded all the data I didn't load from the previous section. But so what I'm going to do is I'm going to open a file. It can produce a standard open dialog, and I'm actually going to open the same chopper thing that I showed earlier. And so there it is in the tree. Everything that you saw before in the Jupyter notebook is there, and I could actually then do exactly what I did in the new Jupyter notebook, which is say print the whole tree. Okay, and I can access. In fact, we share the same history as with, or at least I do. I don't know if it's automatic, but you know, so if I wanted to access, well, let's not go there. Okay. But as I say, of course, then now you can just double click to do a plot. Okay, I double clicked on monitor 1 in case you didn't see what I did. If you right click, you get contextual menus which show you exactly what you might want to, what's available to you. And so, for instance, monitor 2 is another monitor. I could plot that. And what I have here is a simple matplotlib window where I can change axes. I can actually swap them if I wanted to, although I'm not going to. In principle, I can modify things within this GUI. So this is just providing different interfaces to what's available in matplotlib. And for instance, you can add things like legends automatically. You can choose either adding your own legend, or perhaps I'm just going to take the group name. And so now I've got something which I can then export to a PNG or PDF file or whatever. Okay. Now the data itself is available through a view data thing, much like in HDF view, I suppose. And this shows you all the features we used in storing that data. Perhaps it'd be more interesting to look at two-dimensional data. So if I double-click this, now I get two-dimensional data. And here I can go and do things like turn log scales on or off. I can choose different color maps. I can even do bicubic smoothing, which actually I can't on this one, I think, but anyway. And the usual X, Y zooms, etc. And here I can actually sort of zoom in, or I could go here to pan mode, and then I can actually, pan around the data. And the cursor thing should work. So this is the matplotlib history, which means if I keep on clicking back arrow or the cursor key, I'll go back to where I was before. Okay. Oh, and if you find yourself doing lots of repetitive tasks, for instance, then there is the scripting window. So if I can either create a new script, or I'm going to use actually, I'm going to open an example script here. Which is this chopper plot. I think we have time. Okay. And if I run this, it runs it basically, you can see that it actually explicitly confers to chopper, although you can make it refer to any, you can have an indirect thing to whatever you selected. And if I run that, in this case, it just chooses to plot cuts in 10-degree intervals through the list. Okay, so, okay, I'll show more. Well, I'm not sure if I will show more sophisticated scripts. You can see we've developed a lot of scripts over the time to do anything from simple plotting to major data analysis. Okay. Oh yeah, one thing I wanted to mention, by the way, is that so Nexus has the concept of links. They're not always implemented. So HDF5, of course, has the concept of links. You have, in principle, most data is stored as hard links. You could have soft links, or you could have external links, and we use all of those. But for instance, in here, this polar angle actually is a link to another object. That's what this chain link icon means here. And so I can do show link and say, what is that? Well, actually, it's something that's stored in this instrument detect group. So it's buried down here in a place that we need for other purposes. And the time of flight link is buried as well. If this were an external link, it would actually open the file that contains the linked data, and we'll open that. But anyway, so that's so there are lots of niceties you can put into the GUI. And then I think the other thing I wanted to do was to show that you can import data from other sources. So we have a number of import readers. Here's the one for importing spec files. Now, X-ray scattering friends will know exactly what spec is. It was formed at one time as sort of de facto standard for running scans, using these sort of multi-column outputs for each scan. And so we're using Spec2 Nexus that Pete Jemian and Argonne wrote, and it immediately parses the data, shows 271 scans. I'm going to just import 20 of them. And it puts it in the tree. And now this is being stored as a Nexus object, which you could save to a file if you want. Incidentally, actually, this is one thing I didn't show in the demo. I forgot to make a note of it. This is actually stored entirely in memory. Okay, it's not actually stored in a Nexus file at all. Until I save it. And that's because the Nexus format allows you to essentially create the whole hierarchy in memory before you actually save it to a file, if you like. That each one of these scans represents different kind of data. So here's just a simple peak. And every time you plot a one-dimensional data set, we actually add a fit button, which gives us an interface to this LM-fit thing that I showed. And that allows you to, for instance, plot a whole variety of functions. These are all the functions that LM-fit provide. The tooltip shows you actually what the function is. I'm going to choose just a Gaussian in this case, and I can add that. I can go fit, and I can plot the model. And so I fitted this scan within a few seconds of opening the file. But of course, spec files can have mesh scans. So if it's two-dimensional, Spec2 Nexus picks that out and shows it's two-dimensional. And in this case, it has some funky negative y-axis, so I'm going to just flip that. Okay. So this is quite a convenient way of looking at spec files, if that's what you're interested in. Another thing I wanted to show, another very common use case in the X-ray scanning community, and I'm presuming other things, is just to import an image stack. So a lot of experiments, if people store TIFF files or CBF files, we can handle anything that's read by the Fabio module, which is another ESRF module. And in this case, I select a directory, and you can see that it's faded for some reason, I can't remember why, but you can see this file contains actually 400 TIFF files. Okay, and what I want to do is I want to combine them all into a single array. And so I open them, and again, I'm only going to import 20 of them, say. I'll just import 20. And now this is a three-dimensional data set. So we have now a Z tab if you're in Europe, and I can scroll through that. In fact, I can run a movie through that, for instance, and run through all the different TIFF images, but they're now stored as a single three-dimensional HDF5 array. Okay, I need to move on. So what I want to do now is to give two use cases, and they're sort of they're kind of mini stories that reflect the kind of way we do data analysis and the kind of way that NeXpy enables us to do that. So, and the first story involves looking at data from a material called mullite. It's an aluminosilicate, which has a lot of diffuse scattering. So diffuse scattering is when the crystal structure is no longer perfect. And actually, I didn't have to open it, so I can just double click it. But and what it does is it produces a lot of very beautiful patterns in 3 dimensions. So actually, let's just go to, I think I can go to 3 dimensions here. I'm going to put this so you can see the diffuse scattering more clearly. And we can scroll through this manually, which is what we used to do. We try and do other things now. And you can see that wherever you are, you get gorgeous patterns. I could have done a movie, but actually there are too many steps. So I didn't want to waste time. But if we get to, say, this plane here, then we see that we actually have some a whole lot of rather obscure spots. And I'm still in zoom mode here, so let me in pan mode. So let me go to zoom mode. So I might be interested in saying, what do these spots mean? Okay. So if I do a right click and drag over a few spots, then that generates what's called a projection panel. Actually, so you can see this a little more clearly. Let me just and so this is the area which has been initially chosen in this projection panel. And one of the things I might want to know is, are these really 3-dimensional blobs, or are they actually the intersection of rods? You know, this is a 3-dimensional data set. They could be rods coming through. So I'd want to look in the orthogonal direction. And I might say, okay, let's go in the orthogonal direction, which is called QL in this case. And let's plot this. And you can see, actually, yep, there really are 3-dimensional blobs here, 4 of them, in fact, the ones on the side. So the other thing I might want to do is to actually take a 1-dimensional cut through them and decide just to what extent, see if I can understand what the line shape is. And so what I'm going to do is I'm going to just plot a 1-dimensional plot now. You know, this takes so, I don't know why it doesn't. Okay, there we are. It produces 1-dimensional cut. Now, scatterers will know that if you see something like this, these look like Lorentzian line shapes, and the width of that tells you what is the length scale over which there is short-range order in this material. These are technical details. But what you want to know are what are the does it fit to a Lorentzian line shape, and what are the line widths? And as I say, every time you have a 1-dimensional plot, you have a fit button. And so one of the things you can do then is you can fit all of this fairly conveniently So I'm going to add a number of models. So LMFit has the concept of models, as I said earlier, I think. So I'm just going to add a constant background first, which I think of 60 looks if it's good. It's probably a bit high, but anyway, it'll do for now. But I want to then initialize these other plots, and LMFit actually has a very nice way of guessing parameters. So if I actually reduce the area I'm looking at, I can now add a Lorentzian, which will be, and it will guess it just from the area that I've plotted, and so that's not too bad. Now I go back into pan mode and scan over to the next peak. Hopefully this won't take too long. Let me add another Lorentzian. Yeah, okay, it's not perfect, but it's a good enough start. Go into the next peak, add another Lorentzian. And finally the fourth one. Okay, and then let's see what model. Actually, I don't know why it doesn't seem to get this fourth Lorentzian so well, but I might actually remove that Lorentzian and have another go. I think it's because I had this too much of his tail. So I've now only got 4 Lorentzians. Let's go to here. Now let's add the Lorentzian and plot the model. Yeah, that's much better. Okay, so now if I go back to the original axes, plot the data. This is the starting model, and I can fit it, and I plot the model, and it's not too bad. It looks as if it could be improved. In fact, it can probably be improved if I put in an extra background, Gaussian background. And now if I put that, and I plot the model, yeah, that's pretty good. So let's go back to this. Okay, so I've got that fit from the GUI. Now, so this is giving the answer. Sigma is the width. They all seem to have roughly the same sigma. I know what the length scale is. Now I want to save this, okay? And this is where I think Nexus, the concepts of Nexus really come to their own. Because what I can do is I can now just say save fit. And let's get rid of this now. And what it's done is it's actually opened a scratch area, and it's put here this F2, which contains all of the features of the fit. So I can actually, I'm going to actually save this data first because I want to do that. Let me go to options here. I'm going to add this plus button so it'll save this data, and that's gone into S2 here. So this is like a scratch pad, and you can sort of look at the data now, and you can overplot the line, and it's all stored for. And what's more, what I could do now is to create another Nexus file. Say I call it NXFits, and I'm going to, and what I want to do is I actually want to cut this data here, cut it, and I'm just going to paste it in here as fits. Okay. And now all that data is stored within this file. And then I'm able to take the data, which this is just the original data we used to plot, and I say, okay, I want to keep a record of that as well. So I cut this, and I paste that. And I'm going to call it data, say. And then I can save this to a file. And I have, in fact, I did this yesterday, but so I overwrite it. And now I have a complete record of this earlier data analysis I did for future reference, and I could put multiple fits in here if I wanted. And one nice feature is I might come back a little while later and say, actually, I really wanted to do some a different type of fit. The whole thing, you can reload the whole model as you had it before and redo the fits. So Nexus, the message of this is that Nexus is often thought of as being a rather rigid format for storing archival data, but actually it gives you a framework for storing lots of different data products in a very flexible way for personal use or for sharing with your group, because you can just store essentially as a container where you can dump whatever information you want. I could, for instance, copy the sample information, which might have temperature in it, say, and into here just for completeness. Okay. Now I realize I wanted to have some time for questions. So there's one other use case I wanted to show. Let me see if I can do that fairly quickly. I'm going to remove all these things here. So in addition to opening files, you can actually open whole directories. And we often collect a lot of data as a function of some parametric variable like temperature. So I'm going to open this whole directory. These are all the files in there. I can choose which ones I want. This actually represents something like a terabyte of data. So you saw it actually loaded almost instantly. And that's because technically we reduce the latency by only loading the top level and the remaining levels when you need them, but it's still fast. And now I can plot some data. By the way, a lot of keyboard shortcuts. So I'm typing L to get this as a log plot, if you're wondering how I suddenly did that, rather than having to go to Signal and clicking this. Now, this is a material which I happen to know goes through a phase transition. That means that there are lots of peaks here. You can see a lot of peaks here, but they disappear above this phase transition. So I might want to create a new plot and compare it to data taken at another temperature, say. Okay. And what you want to do is to be able to compare this data. So what we have is one way of doing that. It'd be tedious to keep on scrolling through different frames here, for instance, and then changing the limits. But what you can do is you can synchronize the operation so that by creating this limits panel, now I can create the limits panel here as well. And for the second limits panel, it's given me the option to actually copy the limits from the original data set. And in fact, I can even synchronize them. Okay, and then I go here. And what that means is that I can do things like, change which axes I'm plotting against. This is a three-dimensional data set. I didn't take, let me see, one of these. I think so my cursor size is making it, okay, there we are. So it's now changed it to be H versus L instead of H versus K. I can change the which frame I'm looking at for the Z-axis. And what we see is that there are some layers, let's increase the signal, where you have lots of peaks at low temperature and they're all gone at high temperature except for these sort of fake smudges, okay? And so this just facilitates comparison of the data. And I can open a projection panel with a right click like that, and I can actually do the same thing as I did with the limits. I can actually copy those limits. And so now if I wanted to do, say, a one-dimensional plot through here, these pull-down menus are taking a while to read. There we go. I can plot, and we can see there are various peaks here. If I go to figure 2 and I copy the limits, I can overplot, and we see the peaks are gone. But actually, they've been replaced by this sort of these short-range order peaks. So they're not gone entirely. They're just very, very weak. Okay. So we can compare data sets in this way. But what we really want to do now is to understand what on earth is going on as a function of temperature. And let's get rid of all this. So we have all of these data sets which are loaded here. The way we can compare all this data is to use a different panel called the scan panel. And what the scan panel does is it allows us to define what's varying from one file to the other. So all these files have an identical layout. And in particular, for instance, the temperature is stored in this sample area. So if I select that scan, it uses the path to that file. And the same path will work in every file. So if I put in here, I can choose all these files. And I can save that data immediately to the same scratch area that I showed before. And this is this S2. And what you can see is that whereas in the original data, if I go back to, whoops, to this original data. Why did it keep opening that? My cursor size is so big for clarity, but it's making it impossible to. Okay, so if I was to view this data with the view data command, you see I've got these 1201 by 1201 by 1201 arrays. Okay. Now, if I go to this data, it's 1201, 1201, 1201, but it's added this extra dimension. And the reason it's done that is the magic of virtual data sets in HDF5. So it's actually consolidated. It's not actually copied any data. It's just produced pointers to all of these files and the data sets within those files, such that I can now actually plot this in here. And this third dimension now, we've now added a fourth dimension, which is temperature. Okay. And so I can either, so I could go back to here, and I nearly finished. This is the thing I showed earlier, I think, but I can now see, directly compare what happens if I go up to 150. All the peaks are gone. And what's more, I can now use the projection panel on this multi-dimensional data set. So if so I've got all these peaks, and I want to know just how do they disappear. Well, the way to do that, and I'm trying to, I know there's one peak which is particularly nice to look at, so I'll look at that one if I can. I think it's this one. I can sort of do a right-click zoom on this one peak, say, produce the projection panel, and now one of the features is temperature. So I can now plot just against temperature, and it's integrating over all the remaining items here. I need to make sure that I've got a temperature range here. And can I plot? Nope, it didn't take. It never seems to take. Okay, there we go. And so this is exactly how the temperature dependence of that, taken from all of these different data sets, to produce us a reasonable idea of what is the critical temperature, what is the temperature dependence of that peak, and et cetera, et cetera. Okay, so I think that's probably where I should end. Just with a simple summary, that what I hope to persuade you is that actually having a very simple GUI, which just bolts together very commonly used tools in the Python community, PyQt, Matplotlib, and IPython. It gives you really a powerful interface to processing data, and this is big data. So I mean, I'd actually loaded that all these files which are loaded here represent something like a terabyte of data. Okay, through external links mostly, but nevertheless they represent a terabyte of data, and yet we've been able to cut it down to a manageable size for us to extract information. Now, we're also working on machine learning, which is another way of approaching these kind of big data sets, but that's a different story altogether. One thing I didn't let me quickly say is, if you go to here, there are help features available. So if you open NeXpy Help Online from within the application, it goes to the GitHub pages, which explains both the Python interface and the graphical user interface that I just described. And then if I go back to here, there is actually an API tutorial online, which is actually a Jupyter notebook. And you can run it actually online directly within Google Colab. So I can run all of this. And this will demonstrate just what you can do within the Nexus format itself. How you can manipulate fields, how you can create data sets, etc., and then things like how to produce plots. Okay, so I think I should stop there and invite. Whoops, what I'm trying to do with my summary, and invite any questions. Actually, I can't see the chat, so if anything does.
Sure, and feel free to unmute and just jump in if you have a question, or put it in the chat and I'll read it.
I'll stop sharing for now so I can see people.
Hi, go ahead.
Yeah, thanks for the really nice talk. Just about the links with the files, are they just always like full paths, or can you have relative paths, or?
Yeah, you can choose. So there is a switch. It always gets. Yeah. Okay. Let me. If I go back quickly here. I need to open up the shell now, don't I? So you can create a link just by saying, well, okay, I'll show the syntax. I don't know if you can see this window actually very well, but if you do NX link, then you just define the target path equals, you know, /entry/sample or something.
You can't see your screen.
Oh, sorry, I'm not showing. Okay, well, anyway, the short answer to the question is that you can, is when you're defining the link, you can define it as being relative or absolute. And the external links, for instance, will be stored as relative file paths. And what that means then is if you actually, but you can change that and you can store the absolute file path if you want. But what that means is that if you have an external link, what use case we have is that we store, we have sort of wrapper files, which contain all the metadata that we want for understanding what we've measured. But they have external links to the really big data files, the 30 gigabyte, 100 gigabyte data files. And sometimes when we reduce data, we just copy those wrapper files to a totally new system. We leave the raw data behind. But if there is reduced data, you might want to copy some of those external links over. And as long as you keep the relative file paths, then it'll just work. You know, external links in HDF5 fail gracefully. If it's not there, it just, you know, you just can't load it. I think I've actually, if I were to share a screen, I think I've got quite a few cases of
Thanks.
These files, let me remove all these. These files actually don't have external links. But if I was to open this file, these files, you can see there are these directories here which have other files. Actually, not too many in this case, but they can have quite a few others. But if I open this, for instance, then this is an external link. Actually, I said you can open, it'll open the file if you want to see whether the external file. I thought that one did exist. Oh, it's this one I need to open. Sorry. It actually opens the file itself, but it's defined. I don't know if you can see at the bottom here. It's defined by this relative file path.
Okay.
Okay. So the target. So the file name is just the file path is just relative file path. And now what I've actually done in this case is this is a subset of massive of other data which are left behind on our server, just because I only wanted to plot this file, and so all I had to copy that over, and that just still works. Okay.
Yeah. Cool. Thanks.
If anyone else has any questions, please feel free to pop in.
Yeah, I just had one question for the example and the run through there. I guess particularly and let's just use the last examples that you used. What's the memory footprint of NeXpy look like?
It's not NeXpy as well. Okay, so okay, actually, okay, that's something perhaps I can quickly, if I'm not impinging on people's time. NeXpy has the concept of only loading what it needs. Okay, so so the large data arrays are usually not loaded, and you have to access them through slabs. Now, there's a preferences panel here, for instance, and you can define your memory link, so your memory limit. So this is now 4 gigabytes. If you try and load something which is bigger than 4 gigabytes, then it will complain. It says I can't do that. But obviously, if you loaded a few of them, then you might be pushing things up. But I mean, you can get away. You know, we only ever plot usually some two-dimensional slab out of that data set. So so even though this might represent 10 gigabytes of data uncompressed, say, in memory all we have is the two-dimensional slab. The rest is stored in the file. And so I said you could create data within entirely in memory. If you actually initialized a very large NumPy array and added that to an in-memory tree, then it would actually create a core memory file. But it probably wouldn't take very much memory until you actually started filling the slabs. So, but in those cases, it's obviously best to save it to a file. As I say, we've analyzed about 250 terabytes here, and this is just my laptop. I mean, this is quite an old, it's not even an M1 MacBook. And okay, I think I have 16 gigabytes of memory or something, but it's not huge. But you can change the memory limits if you
Okay.
So I don't know if my email address is put on the webpage, but you're welcome to contact me on rosborn@anl.gov. I suppose I put that in the chat if anybody has any follow-up questions. And please feel free of installing it. So actually, in honor of this talk, I finally bit the bullet and created a release candidate 1.0.0 RC1. It's actually was already up to 0.14.8 or something, so it was getting into sort of Gmail territory as a beta, but it's been stable for quite a while. But that release candidate unfortunately doesn't show up in CondaForge, for instance, so I'll try and release a 1.0.0 fairly soon. But if you have any other questions, then as please, well, these slides will be available, but please contact me.
Yep, I just dropped in the chat, so I'll try to get the recording and the slide deck posted tomorrow. And Raymond, if you have any other information you want to post with that, you can jump in or I can post it. Yeah, so feel free to contact Raymond or you chat on the forum if you want. But yeah, if there aren't any more questions, thank you, Raymond, so much for sharing your time and your project with us. And we really appreciate it.
No, thank you for the invitation. I've enjoyed it. And as I say, if you actually have use cases that are outside the neutron X-ray community that you'd like to explore, then I'm happy to discuss them with you. I mean, Nexus, the committee is always open to new experimental fields, for example, if you actually wanted to use Nexus. But that's a slightly separate question to whether you want to use NeXpy. Yeah, thank you.
All right. Thanks, everyone. Bye-bye.